There are few things as universally captivating as a firework display. We look up, mouths open, as the night sky is painted with fire. But beyond the beauty and the noise, there is a complex and dangerous science at work. This is the chemistry of fireworks. It is a story of precise oxidation, quantum physics, and ancient discovery coming together in a split second of brilliance. The story begins long before modern chemistry labs. We travel back to 7th century China. Here, alchemists discovered a black powder that would change the world, gunpowder. It was a crude mixture of charcoal, sulfur, and potassium nitrate. Originally, its purpose was military, a weapon of war. However, over centuries, this technology evolved. The explosions were tamed and adapted for festive celebrations, giving birth to the pyrotechnics we know today. So what is inside a firework? It's not just gunpowder. A firework is a carefully packed chemical package containing 4 key components. First, the oxidizer, which provides the oxygen needed for the fire. Second, the fuel, which burns to provide heat. Third, the colorant, chemical salts that produce specific hues. And finally, the binder, a glue that holds everything together in a compact star form. Fire needs oxygen to burn. In the atmosphere, oxygen is abundant, but for the ultra-fast combustion required in a firework, atmospheric oxygen isn't enough. This is where the oxidizer comes in. Chemicals like potassium nitrate, potassium perchlorate, and potassium chlorate act as oxygen tanks. They decompose rapidly, flooding the reaction with the O2 needed for an explosion that happens in milliseconds. Next, we need something to burn. This is the fuel. The fuel reacts with the oxygen released by the oxidizer in an exothermic reaction, meaning it releases heat. Common fuels include charcoal, sulfur, and starch. Sometimes carbon-based compounds are used. The fuel is the battery of the firework. Without it, there is no energy source to drive the display. If you mixed these powders loosely, you just get a pile of dust. To create a structured firework, you need a binder. Substances like dextrin or starch are used to hold the powdered chemicals together in a compact form. Alongside this, stabilizers are added. These maintain the chemical composition and prevent unwanted reactions, particularly preventing the mixture from absorbing moisture, which could ruin the firework. At the heart of the explosion is a specific chemical dance called a redox reaction. This stands for reduction oxidation. In this dance, the oxidizer is reduced, meaning it gains electrons and releases oxygen. Simultaneously, the fuel is oxidized, meaning it loses electrons and burns rapidly. This transfer of electrons is what releases the massive amount of energy we see and hear. Let's look inside a professional firework, known as an aerial shell. It's like a Russian nesting doll of explosives. At the bottom, there is a lifting charge to shoot it up. Running through the center is a fuse. Packed around the fuse are the stars, the pellets that become the points of light. And in the very center is the burst charge, waiting to blow the shell apart. The stars are the most critical part of the visual display. These are small, handcrafted pellets containing the fuel, oxidizer, binder, and colorant all mixed together. They are the pixels of the firework picture. When the burst charge ignites, it doesn't just explode. It ignites these stars and scatters them across the sky, creating the patterns we love. The physics of the launch relies on perfect timing. First, the lifting charge ignites, acting like a cannon to launch the shell skyward. As it ascends, a time delay fuse is burning inside. This fuse is calculated precisely so that it reaches the center of the shell only when it is at the peak of its flight. Once the shell reaches its apex, the fuse hits the central burst charge. Boom! The explosion shatters the shell casing. The force ignites the stars and scatters them outward into a circular pattern. This is the moment the potential energy becomes kinetic energy, light and sound, painting the sky in a fraction of a second. But where do the colors come from? This is pure quantum physics. It starts with heat. The combustion heat excites the metal atoms in the colorant chemicals. Excited means the electrons in those atoms jump to higher energy levels. But electrons hate being excited. They want to be stable, so they immediately fall back down to their ground state. As they fall, they release energy in the form of photons, visible light. Different metals have different fall distances for their electrons, which produces different wavelengths of light. To create red, pyrotechnicians use strontium salts, such as strontium carbonate. When strontium is heated, its electrons release light specifically in the red part of the spectrum. It is a common and reliable color in the pyrotechnic palette. Blue is the holy grail of fireworks. It is notoriously difficult to achieve. To get blue, chemists use copper salts. However, the copper flame is fragile. If it gets too hot, the color washes out. It requires precise high-temperature combustion and often needs chlorine donors to stabilize the copper molecule in the flame. A perfect blue firework is a mark of high craftsmanship. For green, we turn to the element barium. Barium salts, specifically barium chloride, are the key. Interestingly, barium compounds often double as stabilizers in the mixture, serving two purposes at once. When you see a vibrant emerald green in the sky, you are watching excited barium atoms releasing photons. Gold and yellow are classic colors. These are created using sodium salts. Sodium creates an intense yellow light. Think of older street lamps. It requires minimal heat to activate. For that glittering gold sparkle, manufacturers add iron filings or charcoal into the mix. These particles burn longer, leaving trails of glowing gold sparks. Beyond color, there are effects like sparkle, smoke, and noise. That bright white sparkle usually comes from burning magnesium or aluminium powder. Colored smoke is created by vaporizing organic dyes. For the noise, the bangs and flashes, titanium or flash powder is used for rapid, violent combustion. Even the specific sounds are engineered. Those high-pitched whistles, they are created by packing potassium perchlorate and benzoate into a tube. As it burns, it creates oscillating gas pressure that screams as it escapes. The crackles, on the other hand, come from granules of unstable chemical mixes that produce rapid, successive tiny explosions. We must respect the danger involved. These are powerful explosives containing highly reactive oxidizers. Improper use leads to accidental ignition. Furthermore, there is an environmental cost. The combustion releases smoke and particulate matter, causing air pollution. Chemical residues like perchlorates can contaminate groundwater, and heavy metals like strontium and barium fall back to the ground after the show. In conclusion, a firework display is a masterclass in applied chemistry. It represents the transformation of chemical potential energy into light, heat, and sound through controlled reactions. From the precise oxidation to the quantum behavior of excited metal atoms, every flash in the sky is a testament to our understanding of the physical world. It is science burning bright,